Welcome to a tutorial on the Make Noise Maths module. So this is a Eurorack module that is described as an analog computer. And I think that's a pretty accurate description. So instead of computing digital values, it'll just compute different combinations of analog signals, be it audio or control signals. So before we go to the front panel, I think it would be helpful to go over a little bit of theory. So I think it's helpful to think of maths as processing a specific equation. And you have 4 different inputs. So for the purposes of this explanation, I'm going to call those x1, x2, x3, and x4, corresponding to the 4 different channels that you have available. And then with each channel, you have a coefficient associated to each value, which is just a scalar that'll multiply the value plus or minus some volts. And these are available via the 4 attenuators in the middle of the module. So I think it's helpful to think of these 4 different inputs with their coefficients. In this case, I'm going to call it A, B, C, and D for those coefficients. So we have AX1 paired together, BX2, CX3, and DX4. Then the maths can provide different kinds of outputs. So it has an OR, a sum, and an inverted output. The OR basically takes the maximum between the 4 different inputs and their scalars. So for example, if A times X1 equals 5 volts and B times X2 equals 3 volts, then it'll output 5 volts because that's the maximum between the two. And it'll take into account all 4 channels in order to determine the max. And again, you can feed gate triggers or CV values into these inputs and get corresponding outputs. Next to the OR, we have a sum, and the sum is exactly what it sounds like. It'll sum up the values. So it'll solve the equation AX1 plus BX2 plus CX3 plus DX4. And what this allows you to do is create all kinds of complex control voltages by feeding any kinds of signals in there and scaling each one appropriately. And finally, there's an inverted output, which is exactly like the sum output, just inverted. And the other little piece of theory I'm going to go over, which will make the module more easy to understand, is this concept of rise and fall time. So this allows you to basically lag process a signal. So the rise time determines how long it takes for a signal to go from one voltage to another, and fall time determines the same thing but in the opposite direction. So rise time is from low voltage to high, fall time is from high voltage to low. And the way the curve goes from the low and high and low, you can determine the shape of that by morphing between exponential, logarithmic, and linear. And this allows you a little more creative control over how the sound sounds. And we'll go over more the concepts of how this rise and fall get used in practice later. All right, so now that we have the theory out of the way, let's go over to the front panel here. And I think it'll be helpful for you to keep remembering those AX1, BX2, CX3, and DX4 and how they kind of sum up together or together. When I mentioned the X1, X2, X3, X4, I mentioned there's 4 inputs. So there's actually 4 channels on the maths here. You have channel 1 on the left, channel 4 on the right, and then channels 2 and 3 are in here in the middle. And there's a lot of different knobs and colors and little lines in here, so it might be a little confusing, but so let's quickly go over the general layout so to demystify this module a little bit. So here on the left-hand side, basically everything to the left of my finger here is channel 1. And everything to the right here is channel 4. And these are basically mirror images. So you have identical channel 1 and channel 4 controls, except for these gate outputs here, which we'll go over later. So I'm going to quickly explain what each jack and knob does, and then we'll go over and do a bit of demo so you can hear it in action. So starting here with channel 1, at the top we have various kinds of inputs. So for channel 1, we have 2 inputs. We have signal input, which you can feed an audio signal or a control voltage signal. Then we have a trigger input, which you can feed a normal trigger signal into. And these are different ways for triggering and creating the function. Below that, we have a cycle button, which you can toggle on and off. And that just turns it into an LFO effectively. So when you turn on cycle, the function will keep on looping. So moving down below here, we have these 2 knobs for controlling the rise time and the fall time. Each one has this independent CV control. There's also this both CV control, which will control the entire function, but this one actually behaves in an opposite way. So like high voltages will reduce the time effectively. And just like we described, you can set the rise time, which will determine how long it takes for voltage to go from low to high. Fall time does the opposite. It determines the time it takes for voltage to go from high to low. And then the shape at which that curve goes from one voltage to another is determined by this knob here. So you have logarithmic all the way to exponential, and then you have this little dash here which determines the linear point. And then over here we have a gate input for the cycle. So this effectively is just a voltage controlled way to trigger the cycle on and off. And then moving down to the bottom here, we have the outputs. So here you have the standard function output, which will output the signal created here. And this is different from these outputs here, which we'll go over later. This one is independent and is non-attenuated, so you'll always get the full signal here, independent of what's happening here. And then here we have a gate output called the end of rise. So every time we reach the end of the rise phase, it'll fire a gate here, which is useful for triggering other modules or even the maths itself. And then if we jump over to the other side, we have channel 4. And I don't have to go through this. You have exactly a mirror image here. So same signal input, trigger input, the rise, fall, exponential, logarithmic, cycle, switch. The only difference is here, instead of an end of rise, we have an end of cycle. So this gate will fire when it completes the whole cycle. So effectively when the fall phase is completed. And we'll go over what these things sound like and what the purpose of all of these things are later when we go over the demo. For now, just want to get over the basics of the front panel. All right, so that covers channel 1 and 4 here. Channel 2 and 3 are much simpler. So you have the channel 2 input here, channel 3 input here. And in the middle here, you have these 4 attenuverters which map to the 4 channels. So you have 1, 2, 3, and 4. And if you remember the equation I mentioned at the beginning, so the AX1, BX2, CX3, and DX4. The A, B, C, and D are basically these 4 attenuverters, and X1, X2, X3, X4 are the 4 channels respectively. So I like to think of the maths as basically just constructing the parameters that feed into these various equations. So channel 2, you can feed a signal into here, but if you don't feed anything into it, it defaults to 10 volts. And for channel 3, similarly, if you don't patch anything, it's normal to 5 volts. And this allows you to put a DC offset if you want to scale your value in a certain way. So if you remember the sum equation, AX1 plus BX2 plus CX3 plus DX4, if you don't patch anything into channel 2 and 3, the X2 and X3 values effectively get set to 10 and 5 respectively. So you effectively get constants to play with. And then you can still attenuate and multiply plus or minus how much of that offset you want to put into your equation. And then speaking of equations, let's go down here to these outputs. So here you have outputs 1, 2, 3, and 4, which will output the 4 channels independently here. And all these 4 are normal to these equation outputs here, which you have OR, sum, and invert, as we talked about. So if you don't patch anything here, the signals will all get fed into the equations I was talking about here. And as soon as you patch something in here, you can effectively extract that signal, and it'll remove it from the equation here, so they won't actually be used in these 3 outputs here. That basically it. That covers the front panel controls. Again, the module seems complex at first sight, but when you think of it as just an equation with 4 inputs and 4 scalars for each input, then it's fairly simple. So you have channel 1, which is slightly more complex, channel 4, which is similar to 1, and then 2 and 3 are basically simple inputs that are normaled to a DC offset. So if you don't want to put anything in here, you basically have 2 scalars, constants that you can use to configure your signal. So the power of the module comes in interacting with all kinds of different signals. So you can use it to create all kinds of complex CV outputs, and you can use it as an envelope follower, an LFO, an envelope generator. So now that we covered the front panel and the theory, let's go over some basic examples. You can hear what all of these functions can do. So the first thing I'm going to do is patch in my filter to the audio output here. And I'm just going to use this as a sine wave because this filter can self-oscillate. So I'll just use it as a simple oscillator for demonstration purposes. All right, so now that we have a simple sine wave going, let's use the maths to control the cutoff frequency, which in this case will just translate into the frequency of the sine wave changing. So I'm going to use maths in Lfo mode, which is the simplest application. So you turn on cycle here. And then the way it behaves as an LFO is that the combination of the rise and fall time. So it'll start off at 0 volts. It'll try to make its way to 10 volts. And the duration it'll take go from 0 to 10 is determined by the rise time. Once it reaches 10 volt, it'll try to go back to 0 volts. And the duration of that is determined by the fall time. And then when it reaches 0 volts, it'll repeat the cycle because the cycle is on here. So unlike a standard LFO, you're not changing the wave and the speed directly. You're sort of changing both at the same time by changing the rise time and fall time, which will sculpt the wave and also set the frequency. And then you can use this logarithmic to exponential continuous slider here to determine the shape of the rise and fall time, which again helps you shape the wave. So I'm just going to patch the clean function output here into my cutoff frequency input here. So I can make the rise time really fast. Similarly, the fall time. Then I can go from logarithmic to linear, exponential. So the other thing we can demonstrate is the rise and fall CV controls. So over here I have a peaks module which is set to work in LFO mode. So effectively I have just 2 LFOs coming out of here. And I'm going to patch LFO 2 into the rise time control here. And similarly for the fall time. And similarly, we can change the both one. We can also test out the cycle gate input here. So I've set the first LFO to be a square wave at a slow rate, so it'll effectively fire gates. So if I patch it into the cycle input here, when the gate is high, it'll start cycling, and then when the gate is low, it'll stop. Alright, so we've pretty much covered the rise fall in both controls as well as the cycle mode, which is the LFO. The other interesting thing we can try is the trigger and signal inputs here. So if I turn off cycle, the function will be controlled by the trigger or the signal here. So again, I'm going to use my square wave LFO here as a trigger, and I'm going to patch that into the trigger input here. What that basically means is that every time it receives a trigger, it'll kick off a function cycle. So you can treat it as an envelope generator effectively. Except the difference between a standard envelope generator and this trigger input here is that as soon as it receives a single trigger, it'll complete entire cycles. So it'll go from rise up to 10 and then back down when it reaches 10. Whereas in a standard ADSR envelope generator, the gate, as long as the gate is high, it'll remain in the sustained stage. In this case, we don't have the sustained stage. But one way we can get around that is by patching our same LFO into the signal input here. And the signal input, depending on where the signal is going, either rising or falling, it'll be attenuated by the rise and fall here. So for example, if you feed a signal, an audio or a CV, and the voltage is going up, the rise time will determine how much that gets slowed down. And similarly for the fall time for when it's falling. So again, I can feed my gate input into the signal instead. So if I have my rise time and fall time all the way down, I'm effectively getting that square wave through. But then I can slow down the rise time and similarly slow down the fall time. So effectively, you can use the maths as a lag processor as well. And what's cool about the signal input is you can feed audio signals into here as well. So that's the output coming out of the morpho gene. So now if I feed that into my signal input here, so let's quickly demonstrate this end of rise gate output here. So if you remember, this goes high when the rise phase is completed. All right, so I've set my module back to an LFO. I have the function output going to control my cutoff frequency again. This time I'm going to patch the end of rise gate into the trigger input of my peaks, which I've set into envelope generator mode. And then I'm going to patch the envelope output into the rise CV control here. So as you can see, you can generate very complex LFOs really quickly, or very complex CV controls in general. And just to explain what's happening here, basically every time the rise phase completes, it'll fire a gate which will trigger the envelope, and then the envelope shape will come out of here and in turn modulate the rise time. So you get these evolving complex CV signals. All right, so I'm not going to demo the channel 4 here because it's identical to channel 1. So you can just use your imagination and you can see how it can get really complex really fast. The only difference is this end of cycle here, if you remember. So this triggers when it reaches the end of fall instead of rise. And you can use these two gates to sort of interpatch the other two. And you can quickly see how you can get exponentially complicated CV signals. So instead, let's cover the outputs down here. So if you remember, these outputs here are the outputs of the attenuated versions of the signal. So what comes out of here is basically AX1, if you remember my equations. Channel 2 is BX2, CX3, and DX4. So if I patch this signal again, you can see the signal that's coming out of channel 1. So the channel 1 output here is an attenuated version. So if I patch it here, you don't hear anything, and then I can increase the A value, which is what I called it, by scaling the signal. In this case, my module here doesn't respond to negative voltages, so it's effectively doesn't do anything when I invert it. But for modules that do respond to all complete voltage range from negative to positive, then this becomes much more useful. And similarly here we have outputs for the other 4 channels. So I can output channel 4, increase the level, turn it into an LFO, and bring it back down. And if you remember, channel 2 and 3 are normal to 10 and 5 volts DC respectively. So with nothing patched in here, I basically have up to a 10 volt signal I can pitch out. So you just get a direct control of the signal. And similarly for 3, it goes from 0 to 5. And that's basically it. So these output the individual channels attenuated. These here output 1 and 4 without attenuation. And then down here you have the 3 different equations that are different combination of these weighted inputs. So again, the OR will just grab the maximum of the 4 weighted inputs. And I say weighted because by default they're all 0 if they're in the middle, so nothing will get added. So you need to add contribution to the 4 different channels depending on what you want to be in this equation here. So in this case I'm increasing the channel 1 contribution to the OR value. And since everything else is 0, effectively we're only hearing channel 1. But for example, if I turn this back to an LFO, if I patch this square wave LFO into channel 2, I can add a bit of channel 2 now. As you can hear, the OR gives me the maximum value, so when the gate is high here, it'll grab one of the other ones, and then when it goes low, the other one becomes higher, so it chooses that one instead. And similarly, some will sum up the 4 signals together. And you can change the level for each one. So I can patch another LFO into channel 3 here. And I can bring up channel 4 as well. So effectively I'm mixing 4 LFOs now. We have the 2 maths LFOs and the 2 peaks LFOs. And again, the inverted output is the inversion of the sum. And in this case, my module again doesn't respond to negative values, so I'm going to invert these values here. And effectively I get the same thing as the sum. So let me patch in the morphogene just to get a different kind of sound going. I can patch one of the LFOs into the slide input. We can go here and mix 2 different LFOs. Channels 2 and 3, then we can grab the sum into the vary speed, for example. We can add contributions of 2 and 3. And we can use the CV output of the morphogene and feed it into the rise time control here. You can grab the inverted sum into the morph control. You can grab the ORD signal into the gene size. So we can use the end of cycle here to trigger my tip-top 1 sampler here. Then we can use this LFO here to control the pitch of the sample. Right, so hopefully that gives you a good idea of what the maths can do. So I couldn't cover everything in a short video like this, but I think once you understand the basic concepts, you can get a pretty good intuition of what the module can do. But that's only the first step. Then you need to figure out what to actually use it with. And that's the phase I'm currently in right now. So I'm still learning and trying to figure out how to best utilize all the different functionalities. But as I learn, I'll hope to post lots more demo videos for this module in use. So thanks for watching, and if you like this kind of stuff, be sure to subscribe and like and share it with your friends, and I'll see you guys in the next one.